Hi everyone, welcome to our bonus episode. So far I covered Newtonian mechanics. We started with 1D kinematic equations, 2D kinematic equations, where we started out from Galilean equations and we did Newton's equation. And then we did forces, which were Newton's laws, energy, which is the work being done to a force, linear momentum, where it's a reenactment of energy in vector form. And then we did rotational kinematics and rotational momentum. It's the same stuff again, repeatedly, it's just in the rotational world. What you're going to be learning now is we're going to be dealing with curves, and we're going to be doing straight line segments, like straight with using linear. We're going to solve calculus by using linear equations. So all that stuff with matrices that I showed you will help. If you remember our systems of linear equations, or systems of linear equations, that stuff is very important for what I'm going to show you. We're going to do Lagrangian multipliers, which is the mathematical foundation of Lagrangian mechanics. To get started, let me do a little quick introduction on multivariable functions. So I have a rule that I came up with. I'm going to briefly go into functions of several variables. I'm not going to go diving into it. It is important, but I'm going to show you my little rule that I have. So for clusters of clusters of variables, leave remaining variables alone while taking the derivative. So a cluster is if you have like the z is equal to xy, which we call this cluster H, or w is equal to x, y, and z, and we call this H. It's my little technique when you do with when you're dealing with taking partial derivatives. This is a section that's known as functions of several variables. So when you take multivariable calculus, which is Calc 3, you're going to learn all about this several variable stuff. And I'm going to explain what a Lagrangian is. So I'm going to do videos on this stuff. Really, all you would have is introduction to functions of several variables, limits and continuity, partial derivatives, differentials, chain rules for functions of several variables, directional derivatives and gradients, tangent planes and normal lines, extrema of functions of two variables, applications of extrema, Lagrange multipliers. I am personally going to do a separate video on all this stuff. Might even just do one with introductions, like the first two, but for this video, we're just going to do Lagrangian multipliers. I will do separate videos explaining multivariables functions. I'm going to explain to you what they are. Before I do that, let me show you some geometry. Let me show you Lagrangian points. They're very interesting. Circular. We're going to do Lagrangian points. I just need something to trace a circle on. Let's see. I'm going to use this duct tape. I'm going to show you what Lagrangian points are. All right, so imagine you have a circle, right? And you could think of this as like our orbital circle. Think of this as an orbit. The sun is always going to be in the center of the circle. As Galileo once said, the sun is in the center of the universe. If you ever watch my short, you'll see what I'm talking about. So with this sun, you're going to have three Lagrangian points. You're going to have lines that go straight across. So the first Lagrangian point, so this is going to be Earth, and then what orbits around the Earth is going to be the moon. I know these aren't perfect circles, but just bear with me. And then what goes past this is another orbit. And you have another planet that orbits around here.
What are you doing, Jeff?
Making a video. So the first Lagrangian point is going to be like between the, so this is the Earth. This is the moon. And then this is Mars. Or whatever you may call it, Mars or anything you want. So these are Lagrangian points. So this right here is known as L2. This point right here, this is L1. And then this point here is L3. And then if you draw a straight line going up, we'll have 2 points exactly here. We call these L4 and L5. So these are your Lagrangian points. I know these aren't perfect, just bear with me here. We can move the point if we want, like right here. I'm going to move this L1 like right here is what I'm going to do. So this is L1. As a matter of fact, I'm going to do a better sketch. So if I draw a perfect circle, call this the sun. We got to make these points right here. Oh, the lines are screwed up. Oh, God. Sorry about that. Let me retrace that again. They're not pointing in the right spots. Let me just use another sheet of paper. So in the center of this entire orbit, I'm going to have what's called the sun. And then here, this is Earth. And then this orbit is the moon. So we call this Earth, moon, and then we're going to have another line that sticks outward. And then we call this Mars. And then we called it, this is our L1, believe it or not, is going to be right here. This is our L1 point. So we got L1, and then this point right here, this is our L2. And then if we go backwards, this point right here is our L3. And then I can do 2 vertical points, and we can call these L4 and L5. And then I can stick them like lines. We call these lines constraint lines. So the lines that stick outward from one point, you can imagine the sun as a point. So from one point to the next point, we call these the constraint lines. And these lines represent a linear equation. So this one could be one, you can think of this as one linear equation, and you can think of this line as another linear equation. It's going to have different, additive properties and different variables being expressed, but this is what we call a constraint line. So that's what these are. I will label them. Don't worry about that. I will label these. So these are called a constraint line. And this is another constraint line. Another constraint line. And then this down here is another constraint line. This is another constraint line. And then if we look down here, this is another constraint line. And then this is another constraint line. Now, what I mean by a constraint line is the fact that any line that exists between 2 points, we call them a constraint line. So basically what this means is you're going to have a curved shape, right? You're going to have a curved shape. A point could be represented as a curve. Between every curved shape, there is some kind of linear segment. There's a linear line between all of the curves. That's known as a constraint line. So it's imagining that you're trying to assimilate, you're approximating non-Euclidean geometry by using Euclidean geometry. It's kind of like using the area under the curve, approximating the area by using a Riemann sum. It's sort of like that, but you're just dealing with circles with straight lines instead of doing curves with straight lines. But usually with Lagrangian multipliers, we like to use closed curves. It usually works very nicely. It can be used for parabolas, but we can also use it for closed curves. The problem with the Riemann sum is it doesn't really work with closed curves. It only works with open curves. So if we had something like a parabola, we could use the Riemann sum. But anything that's a closed curve like a circle or a ellipse, because we can imagine that this is an ellipse. If we can trace the whole thing, we can imagine that this is a giant ellipse that's wrapped around the circle. It's one way of thinking about this. So you can imagine that there's an ellipse around the whole thing. I know it's a crooked ellipse, but well, let's try to do. You can imagine that there's like an ellipse that's wrapped around this entire circle. I could still do a Lagrangian. If I had an ellipse instead of a circle, I could still do a Lagrangian multiplier. Lagrangian multipliers are literally the first thing you would ever learn in multivariable calculus, which is Calc 3. It's not the first thing you'll learn, it's the first transformation you're going to learn. After them comes what's called Jacobian. Jacobians are not really, they're more mathematical. They're not real. There's nothing to do with physics with a Jacobian. I know how to do a Lagrangian and a Jacobian, but I'm just going to show you a Lagrangian because Jacobians don't really work with physics. Lagrangians do, because with Lagrangian multipliers you'll have Lagrangian mechanics. So if you ever take Calc 3, you'll learn Lagrangian multipliers and Jacobian change of variables. And if you ever take differential equations, you'll learn Laplacian transformations. And they're more mathematical. Riemann sum is pretty much the only thing that we use instead prior to using Lagrangian multipliers. I tried doing a video on this last night and I really had a hard time explaining this. I couldn't understand the whole concept with the Lagrangian. But I will share it. So many optimization problems have restrictions or constraints on the values that can be used to produce the optimal solution. That's not a really good explanation on what a Lagrangian is, but what is a Lagrangian multiplier used for? So it lets you find the maximum or minimum of a multivariable function when there is some constraint on the input values you are allowed to use. So it's not really good in this circle expressing. Oops. Sorry about that. It's this tripod I have. All right. Sorry about that. So you can imagine that if this circle is facing sideways, that this is our minimal. This is our minimum. This is our maximum. So you can imagine this L5 is our minimum. And then our L4 is our maximum. Now the way these Lagrangian points in space actually work is in space you'll have things that float around because gravitation does not act in space. Newton would always say it's two planets acting towards each other. It's some kind of an attraction. It's really just space-time is what causes gravity. Einstein once said it. It's space-time continuum. That's what causes gravity. It has nothing to do with planets circling around each other. That was a concept that Isaac Newton said, but it's really because of space-time continuum. If you read the Dancing Woolly Masters and you read the Tao of Physics, you'll see what I'm talking about. So in space, the reason why these are important is because in space there's no gravity. Things tend to float and they tend to like go anywhere they want to go, like they just drift. And if I push this pen, it'll keep going and it'll keep drifting across. So what they want to do is if they put space stations up, they want to use what's called a Lagrangian point. And these points are like the valleys in space. So like imagine if I have a marble and I'm rolling it down. The marble's going to want to go this way, right? But if it reaches a well, it's going to want to stay at the bottom of the well. Like maybe it'll go side to side a little bit, but it wants to stay right at this well because this force is keeping it down. So you can think of it like that. So, and we could call these a gravitational potential energy. Well, I know I didn't space the words out, but gravitational potential energy, well, that's what you can think of as a Lagrangian. So each of these points, once you put something located there, it won't move. And if you ever watch Neil deGrasse Tyson, the James Webb Telescope is right here. This is the James Webb Telescope. They use L2. And L stands for Lagrangians. Okay, so that is the physics behind Lagrangian multipliers. We're not going to be doing Lagrangian mechanics, but it's a method of constraints. That's the idea with using Lagrangian multipliers. We haven't learned the methods of constraints when we did Newtonian mechanics. So you can use a test to test the expected change in model fit if one or more parameters which are currently constrained are allowed to be estimated freely. So it's a strategy for finding the local maximum minimum of a function subject to equation constraints. That's what this is used for. Okay. So the reason why I show you an ellipse is because you could have a Lagrangian function, and I have to show you the textbook because I can't really sketch this out. It's really impossible. I could have a curved shape, right? And then inside the shape I could have points, and then I have like a sheet. You can think of this as your calculus portion of the graph, your nonlinear, non-Euclidean geometry, and then this is your linear algebra, which is Euclidean geometry. Now what it is, it's the relationship, it's the bridge between nonlinear and linear. And it's used by signaling these lines. So the closer these lines are together, the steeper it is. It uses lines to signal curves. Imagine it's sending some kind of a sound. We call this geometric analysis. Now what these lines represent, and I'll show you in 1 second, is contour lines. I'm going to show you contour lines. So contour lines, I'm trying to find really good pictures here. Bear with me. These are impossible to sketch. So this is what a contour line would look like. It'd be like something on a graph on a mountain. These are what they call contour lines. So a lot of times when they do graphs, they'll make the lines closer and closer to each other, so that way they can, because the closer the lines are, the steeper the mountain. And you can get a bunch of crazy graphs like these. These are like your contour lines and everything. So that function is just traced out. You're looking at the top of the, you're looking at a perspective from the top. That's in what they call in a two-dimensional plane, not three-dimensional space. So I'm going to do a couple of problems, at least one with one constraint, to show you how it works. I'm just trying to pull up what I need. In Calc 1, you'll learn what's called relative minimum and relative maximum, which is really the same thing as this. You know what? I'm going to do 2 problems. I'm actually going to do 3 problems, but I wonder if we get a point in this problem. All right, let's do a couple. We're going to do some problems with Lagrangians. So using a Lagrangian multiplier with one constraint. This might be a better example, honestly. I'm not going to show you a circle problem. I think we did a circle problem when I showed you the graph. So what if you had a problem that looks something like this? The f of xy is equal to 4xy. And then you have to know that x is greater than 0, y is greater than 0. And then you're going to have the constraint of x squared over 3 squared plus y squared over 4 squared is equal to 1. You know what? I'm going to do a problem. I'm not going to use this. I'm going to do another one. Sorry. So let's say if I had a curve. I'm going to do a different problem. And the curve is x squared plus, this is for a circle, by the way, x squared plus y minus 1 squared is equal to 9. And then it's going to have points 4, 4. We say the f of xy is equal to x minus 4 squared plus y minus 4 squared is equal to, oh no, there's no equals, I'm sorry. This is subject to the constraint. And then you could say that 2 times, because I think it's just the square root of 4, which is 2. So it's 2 times x minus 4. Well, actually what they did was they took the derivative. 2 times x minus 4 is equal to 2x lambda. Because if you take the derivative of x minus 4 squared, it's just 2. If you take the partial derivative with respect to x, you get 2x lambda. And then these are systems of equations, so if you take it with respect to y, you got 2 times y minus 4 is equal to 2 times y minus 1 times lambda. Now, lambda is a constant. It's a constant in these problems. And one of the biggest things I hate about General Physics 3 is that you're going to learn that lambda isn't a constant, but it turns out that it is a constant in most cases with electromagnetism. But what's nice with Lagrangian multipliers is that lambda is a constant. And it's also a constant, I think, in Lagrangian mechanics. So that's x squared plus y minus 1 squared is equal to 9. We're just repeating this equation is all we're doing. And then I guess if you run values by completing the square and whatnot, you'll get x is equal to 12 over 5. Y is equal to 14 over 5. And lambda is equal to negative 2 over 3. Lambda is a variable, but it is known as a constant. And then if I want to figure out my distance, I take d is equal to the square root of 12 over 5 minus 4 squared plus 14 over 5 minus 4 squared, which is equal to the square root of 64 over 25 plus 36 over 25 is equal to 2. So all this is a circle. That's all that is. Let us do one more one more problem. There is one on a cone. So a cone, this is for a cone. Why don't we do an intersection of a surface? You know what? I'm going to pull up my iPad and see which one we want to do. All right, let's do a cone. We're going to do a couple. We're going to do a couple of cones. Or if you want, we'll do 2 cone problems. So this one's a cone. And then you're going to have z is equal to the square root of x squared plus y squared. And then this is known as our surface. And then our point is going to be 4, 0, 0. And this is a nice problem because both the x and the y are traced. So in case if you haven't seen the last example, this was the whole process of the problem we did. In case if there's a camera problem, so I don't have to re-record. So we have to find the distance, I think. So you could also write this or x squared minus y squared minus z squared is equal to 0. It's another alternative of writing this. So if you want to do the distance, we say that d of x, y, z is equal to the square root of x minus a squared plus y minus b squared plus z minus c squared. And then if you trace it out, just the d of xy, trace it out to a surface, you only end up getting the square root of x minus 4 squared plus y squared plus z squared. And the reason why is because these are zeros. But this is just in the format of z is equal to xy. That's what this format is. It's the z, actually that's a bad, right? There's no comma in between. This is in the form z is equal to xy. That's what this is. If you ever have a calculator and you want to do 3D graphing, you have to make sure that you're in this format. It's very important. Z is equal to xy. Okay. So let's square the problem and see what we get. So if I take d squared, we're going to square the equation. D squared of x y z. So all we did was square this. D squared of x y z is equal to f of x y z, which is then equal to x squared minus 8x plus 16 plus y squared plus z squared. Okay. And then you could also, and constrained, so you know that the g of xy is equal to z squared minus x squared minus y squared. So you can think of this as z. This came from this equation. So if you have z is equal to xy, I don't know how they got the minuses in there, but you could think that this whole thing was subtracted, so I guess they got z is equal to xy, and then you could say that if you move the x and the y over, you have z minus xy, and then if you factored in that -1, you would have z minus x minus y, and then we square that, or we just put a square in here, right? We just add a square in the function. So this is how you would get, so what they did here is, I could show you a little backdoor. So if you know this, I could move this over. So I have z minus xy is equal to 0. And then you can imagine that there's a factor of -1. So then I have z minus x minus y. And then we just slap in a square in the problem. See? This gives you this, just from using this simple backflip calculation. All right, so that is that part. Now we got to do a partial derivative. I'm just going to run through a problem. By the way, this delta means change. Sub x means is the partial derivative with respect to x, so you're going to get 2x minus 8. I'm going to do like a list. So they're just saying if I take partial derivatives, it's going to give me this. All right. And then we got to do g's. All right. Now we got to find a critical point. So you got to know that the change of f is equal to lambda times the change of g, where we know that lambda is a constant. You can't really see that. 2x minus 8i plus 2, we'll do vectors, plus 2yj plus 2zk. Is equal to lambda times negative 2i minus 2j plus 2k. I don't want you to get confused. This is all vectors. I don't believe they're unit vectors. They're just vectors because they have different values. And then we get x is equal to negative lambda plus 4. Y is equal to negative lambda, and then z is equal to lambda. All right, and that kind of follows these. If you notice here, this follows this. So x minus 4 is lambda. We just turned these into lambdas. Okay. Now, satisfied with the constraint condition we get, all right, negative lambda, or negative times negative lambda plus 4 squared, and then minus negative lambda squared plus lambda squared is equal to 0. It's really hard to sketch out a lambda. Lambda squared minus 8 lambda. Lambda squared minus 8 lambda plus 16 is equal to 0. And that, I think, follows... I guess we just squared it is what we did. And then you have to use the quadratic formula. But after you solve the quadratic formula, you say lambda is equal to 8 plus or minus, which we use the earth symbol. 8 is equal to... This is like the earth symbol in the Chinese language. But lambda is equal to 8 plus or minus the square root of negative 8 squared. So this is A, this is B, this is C. It's B plus or minus B squared minus 4AC over 2A. That's the quadratic formula. It's X is equal to B plus or minus the square root of B squared minus 4AC over 2A. And then you label A, B, and C. In geometric terms, in geometric properties, you get the quadratic equation. So lambda is equal to 8 plus or minus negative 8 squared minus 4 times 1 times 16 and divide by 2 times 1, which is equal to 4. And X is equal to 0, Y is equal to negative 4, Z is equal to, let me write it in the list. So X is equal to 0, Y is equal to negative 4, Z is equal to 4. And then you want to find the minimum distance. You're going to get D of 0, negative 4, 4 is equal to, we just plug in Lagrangian points. These are our 3 Lagrangian points. D of 0, negative 4, 4 is equal to the square root of 0 minus 4 squared plus negative 4 squared plus 4 squared, which simplifies out to 4 times the square root of 3. So our answer is going to be D minimum of 0, negative 4, 4 is equal to 4 times the square root of 3. Okay, that is a cone, which looks something like this. Bad sketch, but that's a cone. All right, there's one more problem I might do. As long as it's not time consuming, there is one more I like to do. It's number 29. We just did 28 in this. So let's see if I can find the solution for that one. Nah, it's like the same thing again. We kind of did that. I think one example's good. This is like the same kind of problem. I'm not going to do it. Alright, this is it for Lagrangian multipliers. The next episode is going to be Lagrangian mechanics. It will be the last bonus episode for this season. It will be the very last episode. I don't like to just make final episodes, so I like to make a bonus one. I think 2 examples that we did, well, we did 1. No, we did 2. We did a circle and a cone. I think we're good. Alright, stay tuned. So, in the next season will be sound. Just to let you know, it'll only be 3 episodes. So it'll be very safe and sound to film. It won't be. I think this is episode 14 we're up to. It won't be 14 episodes. It'll just be 3 videos. It'll be very simple. The problem with Newtonian mechanics is it's a very wide topic, so there's a lot of detail to explain. But you're gonna like the next one. It's gonna be the physics side of it. We did some physics when I talked about these sketches with Lagrangian points. This was the physics that I mentioned. The rest of it was just all math. It was all it was all shut up and do the math. That's very important for physics. So I just thought we would just do one math video. The next one will be physics. I mean, every video I made was all physics. None of them was really just math. This one is just math. I have to show you the foundation before you put a house up. Like, I have to show you a foundation before you put a building up. Like, I don't want to just make a building without a foundation. So, we got to start somewhere. Alright, it's been a great video. Thanks.